Okay, so the next test is going to be the comparison test, and here's how this works. You are going to compare your series to another series. This is the series we're interested in. We're going to compare it to another series, and we're going to make sure that it's either smaller than a convergent series this will force our series to converge, or we're going to force our series to be greater than or equal to a divergent series. And this is going to force our series to diverge. So it only works two ways. If you're smaller than a convergent series, your series is convergent. If you're larger than a divergent series, your series is divergent. It's not the case that if you can compare your series to a divergent series and you're less than that, that tells you nothing. Let me say that again. If you are less than a divergent series, you know absolutely nothing because you could be convergent or divergent. Similarly, if you are greater than a convergent series, you also know nothing because you could be convergent or divergent. So these are the only two cases we have: being less than a convergent series or being greater than a divergent series. So let's look at a few examples. Okay, so we look at this problem and we see that limit, if we take our divergence test, the limit would be 1. So this series is divergent, but we'll try to show it using a comparison test instead. The way I like to start these is to just focus on the denominator, and I'll say, well, n plus 1 is certainly greater than or equal to n. I think we can all agree upon that. And then I like to build an inequality in the opposite direction. So n plus 1, well, that's certainly less than or equal to n plus n for large enough n, and that's of course equal to just 2n. So this gives me two inequalities. So when you take the reciprocal of an inequality, the inequality sign flips directions. So this implies 1 over n plus 1 is less than or equal to 1 over n. And the second inequality implies 1 over n plus 1 is greater than or equal to 1 over 2n. So if I take this first inequality and multiply it both sides by n, I'm going to get n over n plus 1 is less than or equal to n over n. If I take the second inequality and do that, I'm going to get 1 over n plus, or n over n plus 1 is greater than or equal to n over 2n. So let me write out what I have here. I have, translating this one to series. N over n is just 1. And then this inequality gives me a different statement. And of course, this is just equal to 1/2. I'll rewrite that. The series of 1/2. So, two statements, both true, but the statement on the top says I'm less than or equal to this series here. This series is divergent because you're just adding up 1 infinite times. Being less than a divergent series tells you nothing. But the second statement, 1/2 plus 1/2 plus 1/2 plus 1/2, that's a divergent series as well. But in this inequality, I'm greater than a divergent series. So this implies that my series diverges because I'm greater than a divergent series. Series diverges. Let's look at another example. So, same deal. I'll try and make two inequalities. First one will be n plus root n is greater than or equal to n. So I'm usually just going to focus on the higher power term, the higher exponent term. And I can also say n plus root n is less than or equal to n plus n, or just 2n. So flipping these inequalities as we did before, we get 1 over n plus root n is less than or equal to 1 over n. On this side we get 1 over n plus root n is greater than or equal to 1 over 2n. And if these are true, it must be true for this series as well. Being a bit lazy with my notation, but I'll fill it in. So again, on the right side, this is a p-series. This is a p-series, both divergent, but only this, well, this statement tells us nothing because this is smaller than a divergent series. This statement tells us something because we're greater than a divergent series. So this implies that our series diverges. Let's look at another one. Seventh root of n to the seventh plus n. I'm going to put a root n here on top. Okay. So building two inequalities. I'm just going to focus on the inside here for a bit. N to the seventh plus n is greater than or equal to n to the seventh, and n to the seventh plus n is less than or equal to 2n to the seventh. So if this is true, this must also be true. Seventh root of both sides. We'll do that on both inequalities. So when I flip it, I get what I'm looking for. Less than or equal to seventh root of n is just of n to the 7th is just n. And then same thing over here. Greater than or equal to, I'm going to say 1 over the 7th root of 2. Let me rewrite that. 7th root of 2 times the 7th root of n to the 7th is just n. I still don't have quite where I'm looking for because I have a root n on top, so I'll fix these inequalities and multiply both sides by root n, and just get root n over 7th root of n to the 7th plus n is less than or equal to root n over n. And then same thing over here. Okay. Simplifying the right sides a bit. Root n over n is just 1 over n to the 1/2. And over here, same thing. Okay, so again, this is a p-series, a divergent p-series, and so this statement tells us nothing. This statement, however, tells us everything. We're greater than a divergent series, so our series diverges. So this is the one that you would include on your test. Let's look at another example, one that's a bit different. Okay, so we don't have to do any crazy tricks on this one. You just have to remember that the range of sine n is the interval -1 to 1. So we can say that this series is less than or equal to 1, or the series of 1 over n squared. And this is a convergent p-series, therefore our series also converges, because we are less than a convergent series. Okay, let's try one more. Okay, I'm going to start this the same way. N squared minus n. I have a minus in the middle this time, so I'm going to build my inequalities a bit differently. So I'll say this is less than or equal to n squared. Actually, I think that's the only one I'll need here. So this implies, of course, that 1 over n squared minus n is greater than or equal to 1 over n squared, which implies square root of n divided by n squared minus n is greater than or equal to root n over n squared. So right now we have our series. N equals 1 to infinity, square root of n divided by n squared minus n is greater than or equal to, and let's simplify this side a bit. This is n to the 1/2 over n to the 4/2. So this is equal to n to the negative 3/2. So our series over here becomes 1 over n to the 3/2. Okay, so it looks like our inequalities are pointing in the wrong direction because we have our series is greater than a convergent p-series. So that's unfortunate. We can try something else. The moral of the story is that you don't always get it right the first time. So we'll just try something else. It's no big deal. So what we should do is try to build an inequality so that it points the opposite direction. Maybe something like n squared minus n is greater than or equal to n to the seven-eighths. Oh, try something else. Let's say the seven-fourths. I'm choosing my exponent so that it's slightly less than 2. Very close to 2, but just a little bit less. And the reason I do that is because eventually n squared minus n is going to be bigger than n to the 7/4. Because eventually this minus n stops mattering, and this is still technically, well not technically, this is higher than this. So this inequality will be true some n large enough, which means this is also true. And then finally, this is also true. Alright, this is n to the 1/2 over n to the 7/4. I can simplify this a bit. 1/2 minus 7/4. This is 4 2/4 minus 7/4, which is equal to negative 5/4. So this is going to tell us that the series root n over n squared minus n is less than or equal to n to the negative 5/4 with series equals 1 to infinity, 1 to infinity, and finally it's less than or equal to the series of 1 over n 5/4. And now this is a convergent p-series. We're less than a convergent p-series, so our series converges. So sometimes you get it wrong the first time, that's okay. Let's try something else. You'll get it eventually. I think that's all the examples we'll do for that.